Okay. One.
Oh my God.
Miss Cleveland to the office, please. Miss Cleveland, report to the office.
Mr. Kaufman, is it true that we're going to be taking exams at home?
No. No. Who told you that?
Mr. King.
I have not been told that.
He said something like a lady had said that we were going to take the exams at home because like the urgency of it.
I don't know anything about that, to be completely honest. The lady that he's referring to has been on maternity leave, so I don't know. Maybe he's been in contact with her. I have not been. So I'm not gonna say Mr. King is a liar. I just have not been told anything about it.
Are we doing completion square today?
Alright. We are. Well, I'm not gonna read these. I taught that on Tuesday. But this is where we left off. This is where we're gonna pick up. Well, good morning. Where's everybody?
I know Maddie signed out. I heard her.
Geez, Jake. Abby, you guys don't gotta sit so far away then. It's okay, you don't have to move if you're already there. So yeah, this is what the classroom's gonna look like.
That's a lot of desks.
Yeah, at least it feels like a lot of desks. It's actually only 23. And all of you guys have been in classes that are much larger than 23. A big part of it is for you guys is the fact that my class is still spaced out with the 3 feet that the CDC recommends. I can do that still and meet it. So here's what I want to show you guys. Obviously, I'm not coming around to check homework today because we talked about how we couldn't really complete the last homework assignment. So I'm not looking for that to be done. But I do want to show you. Now this is what I have currently. I have no intention on making you actually go to these particular seats. This is just for me, for attendance purpose right now. When you guys come back after Easter break, I mean, look, we've been together, how many, I mean, some of you have been together with me for literally 4 or 5 classes. So, like, I'm not going to tell you where to sit. You're a grown adult in my eyes, and correct, you're one step below being a full-blown colleague of mine at this point. So sit where you want. Sit where you want. I know some of us are a little bit nervous about coming back and everybody being a little closer. So obviously there will be spare desks. Your class only totals 18, and I have 23 desks. So there's absolutely going to be some dead space. So you can always grab one of those desks. Like, for example, that one in the back corner there by the bookshelf, that one still has 6 feet spacing from everybody and everything. And I'm sure there will be a few other desks that'll be the same way. I don't imagine many people are going to sit, Jake, no offense, where you're sitting, because once everybody is back, I'm not teaching on this board anymore. I'm going back to that board. Today actually should be the last day of live streaming. Today might actually be the last day of live streaming. We're going to finish up today. We'll do our study guide tomorrow. Monday will be an actual test day. I'll just go ahead and let us have that day to take the test, whether that's in person or at home. And realistically, that gives us Tuesday, Wednesday, Thursday. And I'm not starting a new unit with only 3 days before spring break. That doesn't sound like a good idea. So I'm going to probably use those days to go back and maybe do some review of some stuff in Unit 4, since Unit 4 really kind of kicked our teeth in a bit. Or at least for some of us it did. For others, it went okay. We talked about this the other day on live stream, but just to reiterate, sometimes I think we need to set a realistic standard for what we should be looking to get out of this class, and 2, reevaluating our study habits. Some of us are actually having to figure out for the first time ever that the basics are not enough. Doing your homework and looking things over the night before or 2 nights before is not enough anymore. And some of you are actually just now, actually having to figure out how it is you should study math. And I can talk to you guys about what works for me, but what works for me might not work for you or you or you. So we need to find a way that will. And ultimately, that is one of my major goals of this class, is to send you to college with good study habits, because that's something that I didn't have when I went to college, and I got the absolute crap kicked out of me my first year. I finished, my GPA was a 2.7 my first year. I almost lost my scholarships. I got put on academic probation. And then the next 4 semesters, I made Dean's List. So wasn't because Mr. Kaufman didn't know or wasn't smart. It was just because I never had to study. So I spent that whole first year trying to figure out how to study with teachers and professors who, they didn't care if I passed or failed. There was a class of 500. It was what it was. So that's kind of a big part of what I'm looking for from us. If you are popping off A's consistently in this class with the usual level of work, you might want to start considering an actual field of mathematics. You have a natural talent that is it's an unnatural amount of talent. Let's put it that way. So it is absolutely something that you might want to consider. And those of us that are considering math-related fields, even if we're not doing well, that's okay. You still have time. This isn't a make or break. But if you haven't been thinking about it, maybe it's something that you should consider. Or if you get to college and you decide that the major that you're thinking isn't the major you want anymore, guilty as charged, you know that you might have an option as a backup. I mean, it's statistically now it's like 85% of students, college students, change their major at least once. So, keep it in mind. That being said, let's take attendance here, and we will get started. MIA. Canvas is not working well at all. From what I've been reading about this morning, it's kind of like down statewide. So you guys in here, obviously, you don't need to have the slides up because they'll be on the TV there. And those of us at home, I actually emailed them out. So if you don't have anything or you need something, please let me know. Any questions, anything we want to talk about before we get started here today? Jake?
What's not working about it?
I have no idea. It's just the site's down.
It's working for me.
It's been really spotty for some,
Okay.
so it's working for you right now, which is awesome. I know Ms. Mazaka has been able to get on periodically, but I have not been able to get on pretty much almost all morning. I was able to get our live link set up, and then immediately it crashed after that, and I haven't been able to get back into Canvas since. So, anything we want to talk about? Quiz related. We have quiz 2 up. Unit 5 quiz 2 is up. Nobody stopped by office hours yesterday. Do we have any questions? Anything we want to talk about here? Anybody at home on live stream got a question they want to talk about? Well, it doesn't seem like it. We'll double check just in case I missed something. If somebody does type something in the live stream chat there, I'll double check before we sign it off and make sure. All right, we're going to pick up with where we left off on Tuesday. Where we left on Tuesday, we were talking about the inverse trig inequality, or not inequalities, integrals. Integrals, the inverse trig integrals. We talked about how to use those formulas. And we looked at a couple of different, little kind of sneaky techniques we talked about. If we go back a few slides here, taking a look at it, let's start here with what slide number is this? This is slide number 4. Slide number 4. So this is where we started looking at the different ways that these integrals can be done and how to set up the different formulas. The reason why I want to look at slide 4 is looking at, setting a equal to the square root of a number that's not initially a perfect square. So when I looked at a, we said, okay, we want to do, or when I looked at this one here, we'll set a equal to square root 2. we'll set u equal to 3x. That way du would be 3 dx. So that allowed us to bring in a 3 multiplier, a 1/3 out front, and allow us to do a little bit of manipulation there, right? Just to kind of remember, just kind of jar our memory a little bit of what we were doing. Then on slide 5, we dealt with e to the x. Which actually kind of worked out pretty easily for us. But one thing that we did show with this one, which is something that we did for the first time ever, was when we brought in a constant multiplier, we kept it top and bottom. We kept that top and bottom for that function. And then we reduced it down. Everything went fine for that one there. And then unit 6, or slide 6, is actually probably our more difficult one. This is one we ended with. It took us a little bit longer when we looked at this one. So one of the key things about this one was the fact that the numerator is actually a binomial rather than a single term. So the first thing we did was actually split up that numerator into 2 separate integrals, remember? Now the one on the left side, we actually just did a standard chain rule with. We actually did a standard chain rule with because it doesn't actually match any of the inverse integral functions that we talked about. It didn't match any of those because all of those typically have a constant on the top. And if not a constant, something that we can use u substitution to eventually rid ourselves of. And there's no way for us to do that with the one on the left side there. Meanwhile, on the right side, we did have something that matched one of our integration rules, one of our formulas, right? So we went ahead and did that accordingly. So on the left side, we set u equal to the entire denominator. We used u substitution traditionally on that left side function. On the right side, we went with our actual sine formula, I believe, to set up our second one. Both of these required a little bit of finesse, bringing in constants. The one on the left side, we need to bring in a -2. The other side, we needed to bring in a 1/2 to get rid of that, to get that down to 1. And everything went according to plan after that. You guys remember doing these 3 problems, just to kind of reiterate where we were, where we left off. All right, let's jump into it then. So we talked about completing the square. So the whole goal here of why we want to review completing the square is when we look at all of these different inverse trig formulas, and if you don't want to dig through your notes, page 385 has all those, that table that we talked about before, right? This one right here, 385, has all of them written out there. Good page number for you to put a sticky note on or definitely jot down. It's one that I use all the time. I know I don't have a sticky right now, but I normally do. When we look at all of these, we see that almost all of these have something squared plus something else squared, or something squared minus something else squared in the denominator of these fractions that we're looking at. So completing the square allows us to have and create that perfect square, or at least start that perfect square set on bottom. So let's jump into a problem here, and let's see how we'll use completing the square to help us, okay? So ideally, we should only have to do 4 slides together with the live stream, and then you guys in here, we're just going to do some more practice after that to make sure we're more comfortable, and the kids on live stream, they can peace out and have a relatively earlier day. So let's move on to our next slide here. Let's go on to slide, what is that? Slide 8, I believe. Slide 8 is where we're at now. So when I look at this particular function, the integral of dx over quantity x squared minus 4x plus 7. So when I look at this particular function, the first thing I notice here is 1, it doesn't match any of the formulas. 2, I'm not going to be able to use u substitution on it very easily traditionally. So this is one where it's not going to work with our traditional antiderivative rules that we talked about back in Unit 4. It's most certainly not also going to work very well with our outright, the way it is right now with our inverse trig function. So we're kind of up the creek without a paddle. We don't have a lot of tools in our proverbial tool belt to deal with this the way it's written. Okay? So what we can do, as I do see it is a quadratic, I can go ahead and try to solve this quadratic with completing the square. So that's what I'm going to do. I'm going to set up completing the square for my denominator. So I'm going to do that over here. I have x squared minus 4x plus 7. So I'm going to create the perfect square here for us. This is going to become x squared minus 4x and plus 4. And I'm just going to move the 7 outward. I'm just going to move it outward here, plus 7 here. And what I'm going to do is subtract that 4 off of there. If this is not clear to you, the way I have it written on the board, you can, of course, do it the way that we did it in Math 2, the way I kind of reviewed with us. If you like to do it that way, that'll work just fine, too. So you can set this, of course, equal to 0. Move your 7 to the other side, and then add your 4 to it. That'll be negative 7, so we have x squared minus 4x plus 4 equal to negative 3. And all we're going to do is just bring this back over. So this is going to be x squared minus 4x plus 4 plus 3 back to 0. Is everybody okay with what I'm doing there? Okay. Well, what I have in parentheses is a perfect square. This is the group x minus 2 quantity squared, and then plus 3. If you actually remember, this is how I taught some of you how to get vertex form way back in Math 2. This is one of the ways that you can create the vertex form of a quadratic of a parabola. So we're going to take this, which is equivalent, and plug this in for our denominator instead. So we're going to have dx over x minus 2 quantity squared plus 3. This is a much friendlier version of our function, because this one at least we can manipulate, we can match one of our formulas here for the inverse trig functions. The one I'm looking at particularly, the one that we might be looking at particularly here might be like for arctangent, something along those lines. Are we all okay here? So if I want to pick this up and use this for arctangent, which is something squared plus something else squared, right? Now I know that down here it's a squared plus u squared, but of course addition doesn't matter. It could be u squared plus a squared, right? So the order there isn't very particular as opposed to the other two formulas. So if we're going to set this up, a is going to be square root 3. U would be x minus 2, which makes du just dx. Are we all okay with what I've done there? Just setting up the arctangent formula from this substitution. And everything should go according to plan. We're going to have du u squared plus a squared. So that's our standard application of the formula. That should be 1 over a arctangent or tangent inverse, whichever version you like to go with. And that's going to be u over a plus c. The only thing here is we do want to switch back to x's. So a here, this is going to be 1 over square root 3 arctangent u, which is x minus 2 over square root 3 plus c. Are we all okay with this? We're all comfortable here. You can see why completing the square does have some uses to it. Back in Math 2, I said it was an outdated antique of equation, of a way to do it.
And that is true. For solving quadratics, I don't think that completing the square is the way to go. I really don't. Now, I think that completing the square has uses when we reach back to this type of level, when we talk about things in Math 3 or pre-calc in here, but I don't think it's a good way to actually solve a quadratic. I think it's a good way to rewrite a quadratic, which is what we need to do here, what we're going to focus on it with. So maybe Mr. Kaufman misspoke a little bit back with Math 2, but I think you guys can understand the difference here about what we're using this process for now versus what they kind of try to force us to do with it back then. So I kind of laid the framework. Let's try this next slide here. This is slide 9, right? Yeah, slide 9. Why don't you guys go ahead and try slide 9 without me for a second. See how far along in this process you can get. See how far along in this process you can get. It's not that much different. It's not that big of a step from this first. Okay. What do we need to do? First thing to do here.
Take out 1/2.
Take out a 1/2. So when we look at that denominator, we see that there is very clearly a GCF. So it is best to do that first. It's best to deal with that first. Remember how I showed earlier, or on, I shouldn't say earlier, Tuesday, when we did our warm-up problems, right? You guys remember what happens when we complete the square with a number that is not an A value or a leading coefficient that is not 1? We get a lot of fractions. Not that we couldn't do this with a lot of fractions involved. Not that we couldn't. The process, the concept doesn't change too much. It's just that it makes the work, the algebra, the arithmetic a lot harder. And that's where most of us are struggling right now, is with the arithmetic. Now we have this. We want to do our complete the square, right? I like to set it equal to 0, just so that way it mirrors what I know you guys were taught in Math 2. Should be looking at x minus 2 quantity squared and a plus 1. Is that what we got for our completed the square version of us, right? Okay, so when I rewrite this, I'm actually going to take that 1/2, I'm going to take it all the way out. It's nothing more than just a multiplier really at this point, a constant. So I can take it all the way out of my root and make this dx over x minus 2 quantity squared plus 1. This makes a equal to 1. Technically root 1, but root 1 is 1, right? This makes u x minus 2 and du just dx. So we can go ahead and swap this over for du u squared plus a squared. So now we're looking at 1/2 times 1 over a arctan u over a plus c. A lot of this goes away because a is 1, so this is 1/2 arctan of x minus 2 plus c. Is that what you guys got? That's what I got too. If we jump through my work here, that's what everything looks like to me. Relatively easy and straightforward. Relatively easy and straightforward. We're using completing the square to get back to one of these forms, one of these that we can work with. This works exceptionally well, of course, with the arctangent. You can use it for arcsine and arcsecant, but when you use it with those, you specifically want to use it for what's inside the root, because obviously that's where the squared plus or minus the squared is. You do also need to be careful there when you do those, because those formulas are not this plus this. It's not u plus a. There it needs to be u minus a. So you got to be careful with your signs to make sure everything lines up the way you want it to. Okay? But you absolutely could use this same technique for those. It just requires a little bit more, maybe not finesse, but attention. Attention. Okay, so let's jump forward. Last two problems of the day. Last two problems of the day. We've talked about doing integrals with these, all of them being a plus c, so indefinite integrals. So now it is time to start doing some definite integrals. So taking exactly what we have been doing, and just simply having some endpoints for us. So on our next slide here, I have a pretty good one for us. We're to find the area of the region bounded by the graph. We have our function, 1 over the root 3x minus x squared, the x-axis, and these endpoints. In other words, I want you to find an integral from here to here. I've tried to give us some step-by-steps to help us with this because sometimes we struggle. And here are my final 2 steps already available to us, at least us in class. Now, I don't think I actually should have to walk you through this. You guys should be able to figure this out relatively on your own. The only part of this that I think you might need some help with is doing the actual integral itself. And even then, if you read my steps there, I tried to give you a little bit of help. See if you can do it without me actually to start.
Rearrange it just.
So it starts to complete the square. So you put 0 around it. Okay. First step is we need the positive singular. Okay. Okay, it's negative 1, I need negative 1. Okay. And I'll do page 30 up, 30C. Copy into that. Try to go B term, where we will fit. That in the right format, that's not standard form. Okay, well, first thing is improvement squared gives a positive a value of 1. So, we need to get rid of that a. Okay. Second one issue. Like this, right? Both sides. Okay. So when you have this, add it to both sides, you bring it over. Okay. Bring that back to the rest of it. It's gonna be better. See if you've made the same mistake already by not showing enough work. You made the same mistake without showing, because you're not showing every step. I know that gets old because we're in AP calculus, we don't have to show every step. But there is a reason to it at this point. Equal to line number 4. Yeah, bring it all together.
All right, I'm gonna go ahead and I'm gonna jump back in here, help us work this one out. So the first thing we need to do, set up our integral. So our integral is running from 3/2 to 9/4, right? No, wrong. Try again. Which one is the small? Which one is A? Which one is B? 3/2 is 1.5. 9/4 is 2.25, right? Make sure that you have those right. It's not 9/4 to 3/2, 3/2 to 9/4. Make sure that you get those right. Make sure you put them in the right order. That is absolutely something I would do just to try to see if I mess you up, is to put them BA rather than AB. So make sure you're paying close attention. So this is going to run 3/2 to 9/4. Let's go ahead over here. We're going to do our completing the square. So first thing we need to do is get this in standard form. X squared first, 3x second equal to 0. Next thing is, for us to complete the square, we need our A value to be positive 1. It is not positive 1, it's negative 1. So I'm going to divide everything by negative 1. And I've got x squared minus 3x equal to 0. Now I need to create the perfect C value here, negative 3/2 quantity squared. It's going to give me 9/4. X squared minus 3x plus 9/4 equal to 9/4. This is where a lot of people skip the step and they mess something up. This is where a lot of people skip the step and mess something up. X squared minus 3x plus 9/4 minus 9/4 equal to 0. Or quantity x minus 3/2 squared minus 9/4 equals 0. Which actually, what you want to use this for is also 3/2 quantity squared. Sometimes it's easier to not actually square this value when you bring it in. Sometimes it's actually easier to leave it in this b/2 quantity squared format. This is one of those situations where I think it is beneficial. Of course, the last problem, it didn't matter because it came out to be 1, right? So, now that we have this set up, we're going to rewrite our equation. 3/2, 9/4, dx, root x minus 3/2 quantity squared minus 3/2 quantity squared. If I want to set this up using one of my formulas, this is looking like arcsines formula, where I have u minus a. So let's set that up here. U would be x minus 3/2. That makes du dx. That's a nice little substitution for us. No issue there. And we'll make a 3/2. Is everybody okay with how we're going to substitute this in? So, at this point, you do have two options. You do have two options, of course. You can convert your endpoints, 9/4, 3/2. You can convert these two values of u. Absolutely can do that. Absolutely. And in fact, this one wouldn't be that bad to do. This one would not be that rough to switch that over. Or you can keep them as they are and go back to x. So it's up to you what you want to do after your integral. If you want to leave it in terms of u, you absolutely have that ability to do so. You just need to convert your endpoints over. We've done this a couple of times in the past. I'm only pointing it out because we're going to have lots of fractions involved, and I know you guys don't particularly care for fractions. Or, of course, we can go back to x and use them traditionally. I'm going to go back to x and use them traditionally here, at least for this time. This is going to become here 3 over 2, x equal 3 over 2, x equal 9 over 4, du over u squared minus a squared, which allows us to actually set up the actual integral here, x equal 9 over 4, x equal to 3 over 2, and our integral for sine. This is going to be arc sine of u over a. Is everybody okay with what we've done? All right, back to x then. Back to x, this is going to be arc sine. U is x minus 3 over 2. And a is 3 over 2. Evaluated from 3 over 2, 9 over 4. Or arc sine equal to x minus 3 over 2 all over 3, if you want to simplify that interior of sine down just a little bit. And from here, it's plug in and solve. From here, we'll be plug in and solve. So, from this point, we're going to plug in. When we plug in 9/4, we're actually going to reduce this all the way down to arc sine of 1/2. You can do that on your own. When I plug in 3 over 2, this actually becomes arc sine of 0. And from here, it's just about your trig skills. Your trig skills. When is y 0? At 0, right? And when is sine 1/2? At 5 or 6. So 5 or 6 minus 0, 5 or 6. Questions here? Concerns here? Okay then. You can click our way through. And see what we've done. Let's move on to the next one here. Move on to the next one here. For my next slide, this is actually my last slide of the day. It's actually my last slide, my last problem here. Slide 11, I believe. Yep. I just want us to go back and I want to see, can we figure out this one for slide 11? Can we do the indefinite integral? So we did a definite, which I don't think is, I mean, to be honest, guys, I don't think that this is that much difficult, more difficult than what we were doing already. The majority of this lies in, can you get to the integral, right? From that, it's plugging in numbers and grinding things down. That's not a big deal, or at least it shouldn't be. So going back to where we were, can we get to that point? Can we get to that integral using this function? See what you can do, see what you can come up with here for this one. Since this is going to be our last one here, if anybody has any quiz questions or anything that they wanted to talk about, especially those of you on live stream, now would be a really good time to put them up in chat, so that way we can talk about them before you guys peace out after this problem.
Well. Since we split this up. Want to put plus two. What will we have to do here to where it's plus two? Plus two, and this is, right? Little sneaky trick there, right? Crushing it back there, Jake. I like it. I like it. Where are you at next?
Did we fully understand the tricks that we pulled there, or did we think those up on our own? Did we look at that?
I don't know, kind of just, because when I got the U and the DU, I was like, well, you can't, like, in order to get the plus 2 over here, you have to take it out of the 5.
Mhm.
So then you just have -7 on this side
Yep.
to make it equal 5. Just kind of logic my way through it.
Let's give just another minute or two. One of your classmates did have a question for the quiz, so we'll take a look at that quiz question. They wanted to talk briefly about number 4 from your quiz. It's a shame that you guys didn't show up to tutoring yesterday or office hours yesterday. My dog came home from his first grooming appointment. He was looking very dapper. I would have showed him off. And then I cut the grass, and immediately his white paws started turning green. All right, let's jump into it here. Mr. Kaufman wants to be done for the day, or reasonably done for the day. So, a couple of us figured out those first couple of steps on our own. When I look at this problem to start with, the first thing I notice is that binomial numerator that I don't really particularly like for this style of question. When I look at this outright, this is not going to be something that I can use chain rule on very easily. Not going to be something I'm going to be able to use chain rule on very easily. Though I could try to make that work, it is inevitably going to cause an issue on the back end. So what I'm going to do here is I am going to split this integral into 2 different parts. The integral of 2x, x squared plus 2x plus 2, and the integral of -5 over x squared plus 2x plus 2 dx. So on this first one here, if you recall the problem that we reviewed at the beginning class to get us kind of back in the right mindset, we did this once before earlier in this lesson. And for this one right here, we have x on top and bottom. This one does lend itself better to a chain rule, a more traditional U substitution. However, if we do that with this one, u would be equal to x squared plus 2x plus 2, which makes du 2x plus 2. So I have most of what I need here, but the problem here is I need to bring in a plus 2. And we've never talked about how to bring in adding and subtracting. We've talked about bringing in coefficients, multipliers. We've done that for a while. We haven't really explicitly discussed how we can bring in adding and subtracting. And it's actually, well, as Bianca said, you kind of actually just logic your way through it a little bit. If I need a plus 2 here, I will just affect my other additive here. Negative 5 is the same thing as 2 and negative 7, right? So I'm going to just go ahead and go from negative 5. I'll swap this with the positive 2 and the minus 7. So that allows me to bring in a plus 2 and change this to negative 7. Does everybody see kind of the logic, the trick that we're pulling there? This isn't one that we've really explicitly talked about or done before, so I just want to make sure we're all comfortable with how we've done that. Logically, it makes a lot of sense, okay? I don't want a minus 5, I need a positive 2 and whatever. The other number doesn't matter to me, but I need that positive 2. So that's what I'll do to get my positive 2. This allows a nice, easy rewrite here. This allows a nice, easy rewrite. This will become u to the negative 1 du, which is going to become u, or not u. Let's go over here to this side. I'm getting a little ahead of myself here. So for this side over here, it definitely isn't looking like it's going to be a good u substitution problem here. Because if I try to do u substitution here, I'm going to have to bring in x, and we cannot bring in x's like we do adders and coefficients. So for this one, we're going to go with our complete the square technique, x squared plus 2x plus 2 equal to 0. It's going to give me x squared plus 2x plus 1 equal to negative 1. And this is going to inevitably give us x plus 1 quantity squared plus 1 equal to 0. Is everybody okay with this so far? Good so far? All right then. When I look at this particular problem here, when I try to bring this back in, what do I have to do with it? I see that I can rewrite this negative 7 x plus 1 quantity squared plus 1 equal to dx. But there's something else in the way here. What can we do?
Take out the 7 as a coefficient.
We can take out that negative 7 as a multiplier. I don't want it up there, right? The next thing we're going to do is u and a. And when I set u and a up over here for this one in red, let's do that with pink. U would be x plus 1, which makes du just dx, not negative 7 dx. So I'm going to take this negative 7, I'm going to move it out. And then I can go ahead and do my swap. So this gives us negative 7, 1 over u squared plus a squared du, plus integral u to the negative first du. This is what we're looking for our complete u substitution. Now, these are technically two different u's. So if you want, you can maybe say like, oh, I'll use v for this one or v for that one, or a smiling face, or I've seen some in other countries, they don't really use u's, they use alpha substitution or beta substitution. They go back to the Greek letters. So be careful with who your professor is next year at college, because they're going to probably do it a little bit weird. To be completely candid, there's not a ton of American math professors out there. So jumping into this one here, now we just need to do the integrations. Now we just need to do the integrals. Let's catch my work up on the board here just a little bit. Do right about here. So we'll do the first one, the integral of u to the negative 1. What is that integral going to be? That just should become the natural log of u, the absolute value, right? So let's do that. Natural log, absolute value, u plus our -7 multiplier, right? And what is this one? U squared plus a squared. Isn't that going to be our arctangent? So this is times 1 over a arctan of u over a. And all this plus c, right? The only thing we need to do here is go back to our original x's. And this is where it can get a little confusing. That's why I said sometimes it's better to use like u and b or alpha and beta as we talked about. This is going to become natural log of x squared plus 2x plus 2. The absolute value of that. -7. A is already 1, so that's just 1. Arctangent of u, which is still x squared plus 2x plus 2 plus c. For this problem here, because both of those u subs are the same u, it's not that big of a deal. But if this one was something different, if this one was, let's say, rather than x squared plus 2x plus 2, maybe it was x squared plus 2x plus 3, then we might really want to use that u and v format.
Your second u should be x plus 1, right?
Yes. Thank you. See, this is why, this is exactly what I'm talking about. Exactly what I'm talking about. Mr. Kaufman's dyslexic brain can't handle all of it. That is our final answer. I can't think of a better problem than this last one to sum up what we've done in this unit. I've taken you from doing basics of logarithms and exponentials all the way up to doing some fairly complex formulas. The concepts here I don't think are very difficult. To be completely 100% candid, I don't think any of the concept here is difficult. I think our most difficult concept happened in Unit 3 when we talked about the first derivative and the second derivative test. I think those are our highest level concept ideas. I think the issues with 4 and 5 become the arithmetic. We know what we're going to do. We've wrapped our mind hopefully around what's going on. It's an area problem where it's a slope problem. What makes these difficult, what makes calculus difficult, is it is massive amounts of algebra on steroids. It is the biggest, nastiest algebra 2 problems you'll ever come across, with new formulas and new techniques mixed in on how to do an integral and how to do a derivative. This is actually where most of us are struggling, is with this level of work, because most of us are just trying to make it either prettier or trying to go different routes, or just can't seem to get that work done. Our algebra skills, our algebra base is just not always strong enough to see our way through the entire problem. And I wish I could tell you that I have a fix for that, but I don't. The fix for that is practice. The fix for that is to practice and to do problems. And that's what I would recommend, that if you're not getting the test grades and the quiz grades you want, that's the first thing I would tell you to do, is find more problems to practice. Don't practice ones we've already done. That doesn't help you. Go find new ones to practice. And use those things like integral solvers and all that stuff that I know is out there that I'm sure that we've used from time to time to help us. Use those to help you work on that practice, to make yourself better. Because this will be the last test you're taking at home. Which means if you are using those things, you won't be anymore. Questions? Issues? All right, let's talk quiz. Let's talk number 4. Of course, your homework's on the next slide, by the way. Homework's on the next slide. Let's talk number 4 from the quiz. Number 4 from the quiz is an implicit differentiation problem. We have y times natural log of x plus y squared, all all equal to 0, all equal to 0. Okay, so let's go ahead, let's wrap our minds around implicit differentiation again. What's the goal of implicit differentiation? It says it in the problem, but let's just all be on the same page. When I take the derivative here, what are we looking to see? What are we going to try to do? dy dx alone on one side of the equation, right? Okay, so when you look at this, I see two different parts of this. By the way, not all of this is in this. If I wanted this inside this logarithm, I would have put parentheses around it. So the only thing inside the logarithm is x. So I see a nice product rule here to start. Well, let's use that word loosely. Nice, loosely. So we have a product rule here to start. And I see a relatively easy derivative on this side here. So let's do each of those. So derivative here will bring down the 2y, and then the derivative of y dy dx. So that gives us 1 dy dx we're going to be working with, equal to 0. Let's set up our product rule here, f and g. So obviously the derivative of f will be dy dx. The derivative of g, what's the derivative of natural log x? 1 over x. Okay, so let's take g f derivative plus f g derivative. Okay, so g f derivative, that's going to be dy dx, natural log x, plus y over x, correct? Plus our 2y dy dx. Is everybody okay with this so far? Okay, well, from this point, you just need to do the algebra to isolate your dy dx. So I would move my middle term over, and this is going to be probably the last step I'm going to do. I'm not doing the whole quiz for you. Natural log x plus 2y dy dx, all equal to negative y over x. I will tell you outright, your final answer here is going to be a pretty uncomfortable looking fraction, but you should be able to figure it out. It should be written properly. Make sure you don't make any silly algebra mistakes along the way from this point forward. I hope that this has been helpful. Are there any other quiz questions that we'd like to talk about? Those of us on live stream or those of us here in person before we call it a day?
Number one was like, be sure to state the domain or not.
Find the inverse, be sure to state the domain of f inverse, okay? So when you set up and you find the inverse function of this, right? Obviously, you can't have all of the numbers because where we started, you have to remember what its domain and range were, the original function's domain and range, right? So what does that mean for the inverse's domain and range? We did talk about that briefly about what's going to switch with what. So that's what I'm looking for there, okay? I have that listed right now for Fatima as a 5-point question with 3 of the points for finding the correct inverse function and 2 points for stating the correct domain. Okay, well, double check our live stream chat, make sure we're all good. Seems like we're all set here. Well, gang, I'm going to go ahead and let the live stream kids peace out. See them all sometime next week.